Okay. All right. So I want to do a little bit more with this linear quadratic problem. Now today what I'm going to do is we're going to discuss this. Remember the original problem was that J is 1/2 X transpose TF SF X at TF. You minimize this, plus 1/2 the integral from 0 to TF of X transpose QX plus U transpose RU dt, subject to the constraints that X dot equals AX plus BU with the initial condition X at 0 is equal to X0. Now, this is what's classically known as the finite horizon linear quadratic problem. So this is what's called a finite horizon linear quadratic optimal control problem. Now, when we saw that last time that the solution is the following. We got U is equal to minus B R inverse B transpose times lambda. That was the optimal control. So you see that. But we also saw that we had replaced lambda by this new function. We said Sx plus beta. Now, the one thing that I want to go through in a little bit more detail, because I'm not sure that this was necessarily completely clear, is that we know that lambda at TF is equal to SF times X at TF. That comes from the Mayer cost in this problem, because if I take the derivatives to get the final, if I apply the transversality condition to get the final value of lambda, I get lambda at TF is equal to this. So clearly, if I evaluate this function at TF, that tells me that lambda at TF has to equal S at TF, because S is a function of time, times X at TF plus beta at TF. Now, because lambda at TF equals S at TF, and this quantity right here is SF. It's the final value of this solution right here. So what we get is, we get lambda at TF is equal to SF times X at TF plus beta at TF. So if that's true, then what that says is it says lambda at TF minus SF times X at TF has to equal beta at TF. But this quantity right here is equal to 0 because this boundary condition has to be satisfied. So what that directly gives you is that beta at TF has to equal 0. Now, if you recall, we had this block in here where when we decoupled the system, when we rewrote the system in terms of x and beta, we had x dot and beta dot in the new system was equal to A minus B R inverse B transpose S in here. Here we had this function gamma of S, and then we had minus B R inverse B transpose, and here we had B R inverse B transpose S minus A transpose. And this whole thing was multiplied by X and beta. So we had said that gamma of S is equal to minus S dot minus SA minus A transpose S plus SB R inverse B transpose S minus Q. And what we had discussed was that because the system is linear, this boundary value problem is linear, if I find a solution to the problem, then it is the solution, because every linear system has only one solution, it's a unique solution. So what we did was we said, let gamma of S equal 0. So if I let gamma of S equal 0, what happens is we obtain the following system. We obtain x dot, I'm going to write it out separately now, is equal to A minus B R inverse B transpose S times x minus B R inverse B transpose times beta. And we also end up with beta dot is equal to B R inverse B transpose S minus A transpose times beta. Because I've set this equal to 0. Right? So those are the two equations that come out. Now, this system right here, the differential equation for beta is linear. Okay? And this was something that we had, I talked about at the very end of last lecture. I'm going to embellish it a little bit now. So it has the form y dot equals f of t times y. Now the solution to this system, y of t, because this is a linear system, is equal to the transition matrix of f times some condition on y. That's the general solution of any linear system, right? So if I apply that here, I can set this over here. In fact, let's make this a little bit more general. T and tau, just so we don't get confused with the fact that this is necessarily the initial condition. This is the transition matrix of F. The state transition matrix of F. Has everyone seen this before? Has anyone not seen this? Is there anyone who doesn't understand what I'm talking about right here? Okay? Now, if this is true, suppose I now just literally, I'm just going to do a substitution. If I say let y equal beta and let tau equal tf, what do I get? I get beta of t is equal to phi of this matrix right here. Let's this whole matrix right here. If you want to be really technical about it, it's B R inverse B transpose S minus A transpose of T, and I'm going to stick TF in here, times beta of TF. Right? I literally just substituted. Tau I set equal to TF. I replaced this transition matrix with the transition matrix of that over there. Okay? Now, if that's true, I know that beta at TF is equal to 0, right? So if it's equal to 0, this says that beta of T has to equal 0. Because it has to be true for all T. It doesn't make a difference what the value of T is. T can be anything, right? And I picked the condition at which beta is equal to 0. The only way this can be true, if it's 0 at one point, it has to be 0 everywhere, right? So that further decouples the problem, because now what happens is that beta is equal to 0. If beta is equal to 0, then what this says is it says x dot is equal to A minus B R inverse B transpose S times x. And you can actually see that now what happens is I know the optimal control is equal to minus B R inverse B transpose S, which is consistent with what I have up here. And so I can rewrite that because lambda is equal to S times x. I get minus B R inverse B transpose times S times x star. So what this says is, it says the optimal control is actually a feedback law. It's a feedback law, right? It says that at each point along the trajectory, the optimal control is chosen to be this, where S is the solution to this differential equation that comes out of setting gamma of S to 0. So where S satisfies S dot is equal to minus SA minus A transpose S plus SB R inverse B transpose S minus Q, with the initial condition, or the final condition, that S at TF has to equal SF. This I told you before. This is what's called the Riccati differential equation. and it's typically RDE, the Riccati differential equation. And what happens is that as you integrate this, you have to integrate it from the end backwards, okay? So this is a classic thing that happens in optimal control, is that when you solve optimal control problems, you wind up with this influence of boundary conditions at the end that need to be kind of swept back to the beginning in order to figure out what's going on at the beginning. This is a common thing because the original problem, if you remember, in terms of x and lambda, was a two-point boundary value problem. It had some conditions at one end and some conditions at the other. The only way you could have solved that two-point boundary value problem was, well, you know the solution involves the transition matrix, but you have to somehow integrate using the missing conditions. So you have to do like some sort of a sweep backwards, and then when you see you have to pick the final conditions, integrate back and see whether or not you match the initial conditions. If you don't, then you have to keep adjusting the final conditions until you get the initial conditions to be the ones that match the problem. But I'll talk about that a little bit later. That's a numerical or computational technique for doing this. But what this does is it provides for you a complete way of being able to solve the problem without having to do any kind of iteration, right? When I know the final boundary condition on this matrix S, I can integrate this equation backward and get the solution at the initial time. Now I have S of t. If you solve this equation, if you solve the RDE, you get S as a function of t. And once I have S as a function of t, I can generate this optimal feedback. So the optimal feedback first has to be generated by first solving this equation backward in time. I can't get the feedback. I have the law, but I don't actually know what this matrix S is. Now, in optimal control, we actually extend this to a slightly different problem from this, which is used quite frequently, actually, in regulation processes. So consider this. If you have a problem for which you don't have a finite horizon anymore, but you want to control a process indefinitely. So I don't have a specified amount of time that I want to control this process for. I just want to control it for as long as it goes, right? I mean, you could think of this as like, some sort of a plant which you're just controlling 24 hours a day, 7 days a week, and you don't have any endpoint associated with it. That problem is actually a modification of this problem, and it's what's known as the linear quadratic regulator. Okay, that's a different problem. It's related to this problem, but it's not exactly the same problem. So what we do is when we talk about regulation has to do with control of controlling processes for an infinite amount of time. So regulation is the process, is the control, I should say the indefinite control of a process. So these come up all the time. I mean, in all kinds of different things where chemical engineering does this. There are all kinds of applications where you do regulation. So if I'm going to control the process indefinitely, now the problem gets modified as follows. We call this problem the linear quadratic regulator. Okay? Now, people use these terms. It's also called the LQR. This is what people often refer to it as. Do not confuse the linear quadratic optimal control problem with the linear quadratic regulator. They are not the same problem. One is an infinite horizon problem. One is a finite horizon problem. The linear quadratic regulator is stated as follows. We have a cost function. It's even more, it can be made even more general than this, but this is the classic one that's used. X transpose QX plus U transpose RU. Now in this case, these matrices are always taken to be constant. In the previous derivation, I said that A, B, Q, and R, I took them to be constant, but there was no requirement that they actually need to be constant. They can all vary with time if they want to. But in this problem, A, B, Q, and R actually have to be constant. And x dot is equal to AX plus BU with the initial condition x at 0 equals x0. Now, you can look at this and you say, well, it doesn't look a lot different from this problem over here. But let's look at what happens when we actually start identifying the different properties in this problem. First of all, I'm integrating a cost from 0 to infinity. right? And I've made the requirements. Remember, there are several requirements on this problem which are important for the purposes of what we're discussing here. And so I'm going to restate some of them so that we understand what they are. First of all, the pair AB is controllable. Okay? The pair AQ is observable. R is positive definite, and Q is positive semi-definite. They're really important things, especially now when we're dealing with something that's going on an infinite horizon. Because Q is positive semi-definite and R is positive definite, it guarantees that this cost is going to be greater than or equal to 0, the optimal cost. So what this says is that the optimal cost is going to be necessarily greater than, well, it's going to be greater than 0 because this is positive definite. Now, the fact that it has to be greater than 0 means that in order to integrate this from 0 to infinity, this has to be a bounded value, right? The cost can't go unbounded, right? It can't go to plus infinity. That doesn't make any sense. In order for it to go to plus infinity, what is actually required? There are certain things that are required in this integrand. I cannot integrate a function from 0 to infinity where the integrand, what has to be true about the value of the integrand as t goes to infinity? You know this about integrating a function on an infinite horizon? Is that the value of the integrand has to go to 0. If the value of the integrand goes to any number that's not 0, then this is not going to be bounded. Think about it. If I take the area under a curve, right, and if the value doesn't go to 0, then if the value asymptotes to another value, which is not 0, what's going to wind up happening? I'm going to be integrating something that eventually it's going to go unbounded as t goes to infinity. So it's required that the integrand has to go to 0 as t approaches infinity, right? So what that says is it says the limit as t approaches infinity of x transpose qx plus u transpose ru has to go to 0. But because q is positive semi-definite and r is positive definite, it actually puts an even stricter restriction on it than that, which is that each of those terms has to actually go to 0 separately because of these assumptions that I've made. And so what we get is we get this. We get the limit as t approaches infinity of x transpose qx, that has to equal 0, and the limit as t approaches infinity of u transpose ru has to also equal 0. So given the fact that these two things have to equal 0, and this matrix is positive semi-definite, what's the only way that this thing can actually go to 0? It requires that x of t approach 0 and that u of t go to 0. This is all on the optimal solution. So I'm not writing stars here. I probably should be writing stars. So if these things have to go to 0, well, what do we know? We know that lambda has to equal Sx. Well, if x star is going to 0, what does that tell me about lambda? Lambda also has to be going to 0, right? Because it's got to be true for whatever the value of s is. So the limit as t approaches infinity of lambda star of t also has to equal 0. So if that has to equal 0, then what it says is that the only way that that can happen, if you look at this differential equation, we've got this differential equation, s dot is equal to minus sa minus a transpose s plus sb r inverse b transpose s minus q. So if all this has to be true, then what this says is because lambda has to equal s times x, and x is going to 0, so what it says is, it says the only way that this can be true is if s dot approaches 0 as t approaches infinity. If it doesn't, then these things are not necessarily all going to wind up going to 0. So this is a requirement that has to be there, is that the optimal value of S dot has to equal 0, which means that on the infinite horizon problem, we have to have this. Has to equal 0. Sorry, not S dot, S. Which means this has to be true. Because if this thing is going to 0, then the only way that can happen is if the derivative goes to 0. If it's going to 0, its derivative automatically is going to 0. So what we get is we get this. Now, if you look at this, because all these matrices are constant, right? A, B, Q, and R are constant. Then this becomes an algebraic equation. It no longer has to be integrated because the derivative has been taken out of it because of all the conditions that have to be met on the problem, right? So what we get here is we get this problem, this thing right here, when this thing is equal to 0. You see, this is a purely algebraic system that has to be solved, right? If I give you A, B, Q, and R, you can solve for the value of S. S then has to equal a constant because it's the only way it has to be true for all time, right? The only way it can be true for all time if A, B, Q, and R are all constant is if S itself is a constant. This differential equation right here is what's called the algebraic Riccati equation. Now, the algebraic Riccati equation only arises in the case where you have the infinite horizon situation, which is the linear quadratic regulator. Yes?
S approaches a constant. Is that not violating the requirement that S has to go to 0?
No, I'm sorry. This has to be a constant. I'm sorry. This is a constant.
Oh.
So this has to be. Okay. Okay, now, the solution, it's not only has to approach a constant, it actually has to be a constant. So S star actually has to be a constant. Now, what happens is that if you look at that problem, you can see that this is a quadratic equation, right? This is called the algebraic Riccati equation. We normally abbreviate ARE. So the algebraic Riccati equation is quadratic in S. So there are going to be two solutions to this, right? Every quadratic equation has two solutions. So there are two solutions to the ARE. And it turns out that under these conditions over here that we've done, it's a very, very long proof and very long derivations. I'm not going to do it because it would just take so long to go through it. Is that the two solutions, one of these solutions is guaranteed to be positive definite. And that's the solution that we choose of these two, because the one that's positive definite, what it does is, if you remember that the optimal control has this particular form. Remember that U star has the form minus B R inverse B transpose S times X star. So if you choose the one that's positive definite, then what happens is that the closed loop, because now this becomes a regulation problem, right? It's A minus B R inverse B transpose S times X. It guarantees, if you choose this to be the positive definite solution, of the algebraic Riccati equation, then what happens is that the roots of this matrix, for the eigenvalues, will be in the open left half plane. So what that means is that If the eigenvalues are in the open left half plane, what does that mean? It means that now you've guaranteed that this system is stable, and means that as t approaches infinity, x has to go to 0, which is one of the requirements that we had at the beginning, right? So the only way to guarantee that x star is going to go to 0 is by getting the roots into the open left half plane. And the only way you get the roots into the open left half plane is if you choose the solution that's positive definite. It makes the feedback law stabilize the resulting system in the regulation process. So this is what happens in the infinite horizon problem. And it's different from the finite horizon problem in two ways. One is you don't have to integrate the equation. But, of course, this can become a bit of a challenge, solving this equation, if you have a complicated enough system, because algebraically, if your system is large enough dimension, this becomes a linear algebra problem in and of itself, just getting a solution to this. So for a small problem, this is usually not a big deal. You know, MATLAB has a function called ARE that will actually just compute it for you, or LQR, which will compute the feedback law for you. But in the case where you have large problems, solving the algebraic Riccati equation can become computationally quite difficult. And in fact, in a lot of optimal control problems that are like, if you take partial differential equations, optimal control problems are often used to control systems that are defined by partial differential equations. You wind up having to discretize the partial differential equation in terms of a spatial variable, and then you have a time variable. And normally the discretization on the spatial variable can lead to the finite dimensional approximation having many, many states. So if you have a large dimensional state, then what winds up happening is you get these huge systems, x dot equals ax plus bu, if you're linearizing, where a and b are giant matrices. I mean, they could be hundreds to thousands, in size. So you've got to solve these big equations. So that becomes a computationally very difficult thing to do. For small systems, it's not really a big deal. Okay. Now the next thing I want to do, which is the last thing I want to do today, is I want to go take kind of not a step backwards, but I want to take a step sideways, if you want to call it that. Which is I want to go back to this boundary value problem, because we have this nice feature in the linear quadratic problem that everything can be decoupled. But if you didn't have that, you'd be stuck in a slightly different situation, and you'd have to figure out how to get yourself out of being stuck. So let's write down the problem before. This is the linear quadratic problem prior to transformation. So before I transformed it with the transformation from lambda to beta. So if you look at that problem, you've got x dot lambda dot is equal to A minus B R inverse B transpose minus Q and minus A transpose. And I have the conditions that x at 0 is equal to x0 and lambda at TF is equal to SF x at TF. Okay. Now, if I didn't go through all this excursion, or maybe I should put it a slightly different way. If I couldn't go through all this excursion of being able to solve the problem by doing the transformation that I did in the case of the linear quadratic problem, and I was stuck with this, what would I have to do? I want to solve this problem. What would I have to do? Let's take a slightly different look at this. Let's suppose we let phi of t and t0 be the state transition matrix. So I'm gonna assume one thing in this: the state transition matrix of the matrix A minus B R inverse B transpose minus Q and minus A transpose. Okay? So I'm going to assume something that you can't do on a computer, but you can do it here on the board, which is that my integration is going to be perfect. Okay? I have the state transition matrix because that's the solution to this problem, right? So I know that x of t and lambda of t is going to equal phi of t and tau times x of tau and lambda of tau. All right? Now, given the state transition matrix, which I assume I can compute it perfectly, how am I going to solve this problem? Where is the fundamental issue in solving this problem? Is there any issue in solving this problem? The boundary conditions, right? Well, what's the problem with the boundary conditions? What do I have at the initial time? What boundary conditions am I given at the initial time? X. I don't have anything about lambda, right? So if I'm going to apply this equation to integrate, suppose I set tau equal to 0 in this equation, right? If I set tau equal to 0 and I integrate from 0 to tf, right? Can I do it? Can I integrate from 0 to tf? What's that? Yes or no? No, why not? You don't know lambda at 0, right? So I can't integrate this equation forward in time because I don't know the initial conditions. What about the final? What if I go the other way? Suppose I decide I'm going to integrate from tf back to t, or back to 0, right? So I start at tf and I'm going to integrate back to 0. Can I do that? Why can't I do that? Because I don't know. In fact, I have less information at the final time than I do at the initial time, right? At least at the initial time, I know everything about the state, right? But at the final time, I don't. I only know that the costate is a linear combination of the components of the state, right? Because it's through this matrix SF, and I know this matrix SF. So it basically says that if I just write a linear combination, take a value of x, take a linear combination of it, I can compute a value lambda, but I don't have any idea whether that pair that I've just generated, if I guess the final value of the state, and then I compute this costate, and I integrate backward, then I'm necessarily going to satisfy the initial condition, right? I may not. I may pick a value of the state here at the final time, and that generates this costate for me. Now I have a complete set of final conditions, but if I integrate backward, it may not necessarily take me back to x0, right? The x at 0 equals x0. So I have a problem on my hands that I have missing information at either end. So what do I need to do in order to be able to solve this problem? So what I'm going to introduce you to today, because it's useful that you get this method a little bit early, just so that you can play around on the computer and see how some of this stuff works. It's actually really useful, which is what's called the shooting method. Okay? Now, shooting method is the most basic numerical method for solving optimal control problems. It's not just used for optimal control, it's used for any two-point boundary value problem, but it's used particularly in optimal control. The way it works is as follows, is that you have some time interval, let's say 0 to tf, and you've got some boundary conditions, which I'm going to break into two groups here. These boundary conditions are known. These boundary conditions are unknown. Over here, I've got the same thing. I've got some set of boundary conditions over here, which are kind of fuzzy, because I sort of know some things about them, but I don't necessarily know everything about them. That's the case over here, right? I don't know either x or lambda at the final time. I just know that they're related through this equation right here, right? So what happens is in the shooting method is these are the unknown boundary conditions, and these are the known boundary conditions, or initial conditions. So the shooting method works as follows, is that we make a guess of these unknown boundary conditions. So this is our initial guess. And then we take this whole thing and we integrate. So let's suppose that the optimal solution is the actual boundary conditions are satisfied here. We integrate here. And then what we do is we say, well, actually in this case, let's do it the other way. Let's go backward. So we start here with some conditions some some values that satisfy our boundary conditions, and we integrate backward. We integrate backward, and we get to some solution here. But the optimal solution, or the solution that satisfies the known boundary conditions, is actually sitting here. So what happens is we integrate backward, and we say, well, that didn't hit the known boundary conditions. So what we're going to do is we're going to adjust this value over here to some other value, and then we're going to integrate again to go back to some other value, and we get a new value over here. And what we do is we say, well, are we closer to the known boundary conditions on this trajectory or not? If we aren't, then we have to adjust this thing one way. If we are, then we keep going in that same direction and we adjust again. And then we finally adjust to the point where we do the iteration so that we wind up hitting the known boundary conditions exactly, and that solution satisfies all the boundary conditions, and so it's the solution to the problem. So it's an iterative process. The iteration takes place by, in this case, we'd actually have to do it by picking a value of x at tf and then generating a value of lambda at tf. So we now know that all the terminal boundary conditions are satisfied. Integrate backward and see where we are relative to this value x0. It's not going to satisfy that, right? But then we're going to say, all right, well, based on the value, how far we are away, we're going to generate a new value of x, and then we're going to do this again. Now, we have to do it twice initially, once to get the first solution, another time to get the second solution, and see which one of those actually got us closer. Depending upon which one of those got us closer, we're going to now adjust the values that we chose at the terminal time so that we presumably will get ourselves even closer on the third try. And then we adjust again, and we get ourselves even closer on the fourth try. And then we keep doing that until we finally hit the boundary conditions. As you can see why it's called a shooting method, right? I mean, you're basically like, it's like, pointing a gun or something and just shooting, right? I mean, you're just, target. You're just trying to hit the target. So you have a target, and you keep trying to adjust the direction that you fire. It's like a cannonball, right? Until you actually get to where it is you want to go. So this is a very common technique that's used. And you can see that this is a pretty simple problem. But you can see that there's no way around doing something like this. You need to somehow generate boundary conditions, because the missing boundary conditions. Because if you don't, you can't get a solution to the problem. So no matter what you do, you're going to be stuck having to do this iterative process unless there's a way to do some sort of decoupling and some fancy math like I did in the linear quadratic problem to actually be able to solve the problem without doing that, right? Even in the case of the linear quadratic problem, when I'm all done, I still have to integrate that Riccati equation backward in time, right? But integrating it backward in time isn't as big a deal because I know the final value of it, right? So I can integrate back to t0, so I don't have to do any iteration. All I have to do is just one single integration, sweeping myself back from tf to t0, and I get the solution. In this case, I can't do that. And now what I'm going to do is I want to show you something that is problematic about this shooting method. I want to go through, and hopefully I have enough time to be able to do this. But I'm going to do it for a scalar problem because it's actually easier to show how this breaks down for a scalar problem, which is that let's suppose that we consider the following scalar problem. A scalar problem which is j is equal to SF times x squared at TF, because everything's a scalar here, plus 1/2 the integral from 0 to TF of qx squared plus ru squared dt, and then subject to x dot equals ax plus bu with x at 0 equals x0. Okay? Because this is a scalar problem, it's actually fairly straightforward to do some of this stuff. So I know that the system of equations that comes out of this looks like this. A minus b squared over r minus q and minus a times x lambda. You can just plug those in. You can see that that's what you get because everything's a scalar. Now, because this is a scalar problem, I can actually do some things analytically that are hard to do with a vector equation. I know that this is a linear system. I know that its solution is that transition matrix. What else do I know the solution is? Remember now, this is a system of the form P dot equals F times P, right? Where P in this case is equal to X lambda. What do we know about linear differential equations? What do we know their solutions to be? Yeah, what else? What do we know about the structure of their solutions? No, they're linear. So I want to know some real specifics about their solution. You've learned all this in differential equations, by the way. Maybe you don't remember differential equations, that's a different story, but you've learned all this in differential equations. The solution of any linear system is a linear combination of the eigenvalues and the eigenvectors, of terms involving the eigenvalues and the eigenvectors, right? So I know that the solution to this has the following form. P of t is going to look like this. It's going to look like C1 times e to the mu1 times t times v1, which is the first eigenvector, plus C2 times e to the mu2 times t times v2, where v2 is the second eigenvector. Okay? Where mu1 and mu2 are the eigenvalues. Mu1, there's a reason I'm using mu instead of lambda. Mu1 and mu2 are the eigenvalues of f, and v1 and v2 are the eigenvectors. Assuming, of course, that these eigenvalues are unique. All right? So now I've given you the solution. Now tell me what you need to do. What's that?
We need to find out mu1 and mu2.
Yeah, so how are we going to figure out the eigenvalues? Don't tell me you don't remember how to compute eigenvalues.
Solve the characteristic.
Solve the characteristic equation. Okay, now we're getting somewhere. Okay, what is the characteristic? What do I need to do? I need to set the determinant of mu I minus f equal to 0, right? What is the determinant of mu I minus f in this particular case? By the way, this works out. This works out really nicely. I should actually put another stipulation up here just to make it clear that q is greater than 0, and r is also greater than 0. All right, it'll just make life a lot easier if I do that. Okay, so what happens if I do this? So if I take the determinant of mu I minus f, what is mu I minus f? I get mu minus a b squared over r, q, and mu plus a. And I'm going to set the determinant of that equal to 0, right? So what is the determinant of this? You get mu squared minus a squared minus b squared q over r equals 0, right? I said q and r are both positive. There's a reason why I said q and r are both positive in this, because otherwise this may not necessarily work out. So what's mu equal to? Well, it's equal to plus or minus the square root of a squared plus b squared q over r, right? Now, a squared is definitely positive, right? It doesn't matter what a is. It could be 0 if a is 0. But this term over here is absolutely positive because q and r are positive, and the system has to be controllable, right? So b can't be 0, because if b were 0, the system wouldn't be controllable. And I said already that for the linear quadratic problem, the system has to be controllable, right? So the only way this can be controllable if b is greater than 0, which means that these eigenvalues necessarily have to be what? Non-zero. They can't be 0, right? So because they can't be 0, what else is true about these eigenvalues? What's true then about what's underneath this square root? It has to be positive, right? So these eigenvalues are real. So the eigenvalues are real. Are real and non-zero. So that means that one of these eigenvalues has to be in the right half plane, and one of the eigenvalues has to be in the left half plane, right? They can't both be negative. One of them has to be positive, right? This is a characteristic of these systems that come out of these optimal control problems. That you get the symmetry in the eigenvalues. if one of these eigenvalues is positive, right, then that means that this function, p of t, which is the solution, looks like this. Then p of t looks like c1 e to the mu t, I'm just going to call it mu, times v1, plus c2 e to the minus mu t times v2. Now, let's relate this back to the shooting method that I just described, okay? Because this is really important, because you're going to find that computationally this becomes very difficult when you solve any kind of a meaningful problem in optimal control. One of my eigenvalues is positive. So if I integrate forward in time, what's happening? Remember, I can go back, just do this. This is the same problem that I just described. It's just that I'm doing it for a scalar, right? If I integrate from 0 to tf, what's happening in the solution? It's blowing up, right? What happens if I integrate from tf back to 0? What's that? No, I'm going from tf back to 0. Now what's happening? If e to the mu t blows up in forward time, what happens to e to the minus mu t in backward time? No, e to the minus mu t approaches 0 in forward time, right? So if I'm integrating backward from tf to 0, what's happening to e to the minus mu t? It blows up, right? So it doesn't matter which direction I integrate. It's going to blow up, right? So if I have a problem which is blowing up in either direction of time, and I make an error in the guess at that time, the guess is going to drive me away from the solution, and the longer I integrate, the bigger and bigger that error is going to wind up getting, right? No matter what I do, if TF gets very, very large, that error is going to wind up blowing up, right? So it doesn't make a difference what happens if I go forward or if I go backward, I'm going to wind up blowing up, right? So this is a problem that you have in these optimal control problems, is you have these instabilities that come in. So when you apply something like a shooting method, if you're integrating over a long enough period of time and the eigenvalue has a large enough real part associated with it, you're going to blow up in either direction of time, which is fundamentally problematic, right? Because computationally, the computer can only do so much for you, right? Eventually, if you overflow the precision of the machine, it's going to give you garbage at the output, right? So you have to understand that when you solve these problems computationally, you can't just naively just do this integration, because if you have a complicated problem, you're not going to be able to integrate in such a way that you keep the errors sufficiently small unless your guess is good enough. And even if your guess is really, really good, if you're integrating over an extremely long period of time, you're still going to wind up blowing up if you made any error in the guess, because the integrator itself introduces an error because it's not perfect, right? So no matter what you do, you wind up with this instability. So that was the last thing I wanted to talk about today. It was just for you to understand that the shooting method looks great on paper until you actually get into the fact that, well, there's more to it than that because you have these instabilities. We're going to talk about this next week. Oh, by the way, I'm going to make up a lecture next week. I'm going to record it off the regular time. I have to talk to the Edge office about doing that because I'm going to be at a conference on Monday. So probably like Thursday next week, I'll record the extra lecture. So we'll have class Wednesday and Friday, and then we'll have the extra recorded lecture whenever they can schedule it for me. Okay?